3 in the afternoon, November of 1944, a hard stand on the island of Saipan in the Mariana Islands of the Central Pacific. The temperature is 94 degrees Fahrenheit, and the humidity is suffocating, and the coral dust kicked up by every taxiing aircraft hangs in the thick tropical air. A B-29 Superfortress, named Slick's Chick, belonging to the 73rd Bombardment Wing, sits on the hard stand with the cowling removed from its number 3 engine. A crew chief named Earl Dabney, 26 years old, from Tulsa, Oklahoma, is standing on an oil drum because there are no proper work stands on Saipan, reaching deep into the engine to pull spark plugs out of the rear row of cylinders on a Wright R-3350 duplex cyclone radial engine. There are 36 spark plugs in this engine, 2 plugs per cylinder, 18 cylinders, arranged in 2 rows of 9. The 5 upper cylinders of the rear row are the ones that matter because those are the ones that run hottest, the ones that the cooling air reaches last and weakest, the ones whose plugs foul and burn and fail faster than any others. On the early engines, those upper rear plugs have to be pulled and inspected and often replaced every 25 hours of engine running time. And the cowling on these early B-29s was designed so badly, with such tight clearance and no proper access doors, that to reach the plugs on the rear cylinders, the ground crew often has to pull the propeller and strip away large sections of the cowling first. A job that should take 20 minutes takes hours. Earl Dabney does this job, or some version of it, every single day, in the heat, on an oil drum, with coral dust in his eyes. The spark plug he pulls out of the number 8 cylinder is fouled. There is a hard, gray-white crust of lead deposit bridging the gap between the center electrode and the ground electrode. The plug has stopped firing. He holds it up, looks at it, sets it in a marked tray, and reaches for a fresh one. The fresh plug is small, no longer than his thumb, a precision assembly of steel shell, ceramic insulator, and metal electrodes. Stamped on the shell is a manufacturer's mark. The mark says Champion, and the small ceramic and metal object in Earl Dabney's hand, which he treats as a consumable, logging it in and logging it out like a washer or a cotter pin, is one of the most quietly demanding pieces of engineering in the entire airplane. Because that spark plug has to do something that almost nothing else in the engine has to do. It has to sit inside the combustion chamber of the most powerful and most overheated production engine in the world, and it has to survive temperatures that approach 2,000 degrees Fahrenheit. And it has to keep firing, spark after spark, 50 times per second, while the metal around it glows and the lead fouls it and the cylinder tries to cook it to death. When people think about the B-29 Superfortress, they think about the big things. They think about the airplane itself, the largest and most sophisticated bomber of the Second World War, pressurized, remote-controlled gun turrets, the airplane that would carry the atomic bombs to Hiroshima and Nagasaki. They think about the engines, the giant Wright R-3350 radials, 4 of them, each displacing nearly 3,350 cubic inches and producing over 2,000 horsepower. They think about the famous overheating problem, the engine fires, the magnesium crankcases that burned with a fire that water could not put out. The B-29's engine troubles are well documented and frequently discussed. What almost nobody thinks about is the spark plugs. And yet the spark plug was, in a very real operational sense, one of the limiting components of the entire B-29 program. The engine could not run without spark plugs that worked. The spark plugs had to fire reliably inside a combustion environment, more hostile than almost any spark plug had ever been asked to survive. They fouled constantly because of the lead in the fuel and the engine's tendency to run cool and rich at the wrong moments. They were brutally difficult to access for replacement because of the cowling design, and they had to be replaced so often on those critical upper rear cylinders that spark plug maintenance became one of the single largest consumers of ground crew labor in the entire B-29 operation. The airplane that won the Pacific Air War ran on spark plugs, and the spark plugs ran at the absolute edge of what spark plug technology of the 1940s could deliver. This is the story of that small, overlooked, desperately important component, and of the company that built the plugs that could survive the inside of the most demanding engine in the world. This is the paradox at the center of the story. The United States, in the early 1940s, built the most ambitious aircraft engine in the world, the Wright R-3350, an engine so powerful and so advanced that it strained every component technology it depended on to the breaking point. The engine pushed its cylinders, its valves, its bearings, its cooling system, and its spark plugs harder than any production engine had ever pushed them. And the spark plug, the smallest and cheapest component in the entire engine, turned out to be one of the hardest parts of the whole system to get right. The most powerful engine in the world was held back, in part, by the difficulty of making a piece of ceramic and metal the size of a thumb survive the conditions inside its own cylinders. The resolution of this paradox lay in the specialized industry of aviation spark plug manufacture, and specifically in the Champion Company, which had been making spark plugs since before the First World War, and which had spent decades learning how to build plugs that could survive inside aircraft engines. The challenge of the R-3350 spark plug was not a challenge of inventing something from nothing. It was a challenge of pushing an existing, mature technology to a new extreme, of finding the exact combination of insulator material, electrode metal, internal geometry, and heat range tuning that would let a spark plug survive inside the hottest cylinders of the hottest engine in the world and keep firing. The engineers who did this work were not famous. The plugs they made were treated as consumables, thrown away by the thousands, logged in and out by men like Earl Dabney on oil drums on Pacific Islands. But without those plugs, the engine did not run, and without the engine, the airplane did not fly. And without the airplane, the Pacific Air War is a different and longer war. The popular history of the B-29 is a history of the big things, as the popular history of every weapon is a history of the big things. It is a history of the airplane and the engine and the missions and the atomic bombs. It has nothing to say about the spark plugs, because spark plugs are not photogenic, are not attached to any famous mission, and are thrown away by the thousands without ceremony. The men who designed them are anonymous. The company that built them is remembered today, if at all, as a maker of automobile spark plugs sold at parts stores. The specific engineering achievement of making a spark plug that could survive the inside of an R-3350 cylinder has vanished entirely from the popular memory, even as the engine's overheating problems are discussed in every detailed history of the airplane. This is the pattern of the deepest layers of industrial warfare. The visible parts, the airplane and the engine, get the attention. The invisible parts, the spark plugs and the bearings and the valves and the seals, do the actual work of making the visible parts function, and they get no attention at all, because they are small and unglamorous, and they do their work silently inside sealed assemblies where nobody can see them. The spark plug fires inside the combustion chamber, where no eye can watch it, 50 times per second, and if it fires correctly every time, nobody ever thinks about it. It is only when it fails, when the engine misfires and loses power and the bomber struggles for altitude over the Pacific, that the spark plug becomes briefly visible as a problem. The story of the B-29 spark plug is the story of a component that was essential precisely because it was reliable, and forgotten precisely because, most of the time, it worked. To understand the difficulty, you have to understand what a spark plug actually does and what it has to survive. A spark plug is the last component in the ignition circuit of a gasoline engine. Its job is to convert the high-voltage pulse from the magneto into a spark that jumps across a small gap inside the combustion chamber, igniting the compressed mixture of fuel and air at exactly the right instant. The spark plug has a center electrode, a rod of metal that carries the high voltage down into the combustion chamber, surrounded by a ceramic insulator that keeps the current from grounding out against the metal body before it reaches the gap. The insulator is housed inside a steel outer shell, which screws into the cylinder head and carries the ground electrode. The spark jumps from the center electrode, across the gap, to the ground electrode, and that spark ignites the mixture. The environment inside the combustion chamber, where the firing end of the spark plug lives, is one of the most hostile in all of mechanical engineering. Every time the cylinder fires, the firing end is engulfed in a flame front that can approach 2,000 degrees Fahrenheit, and the pressure spikes to hundreds of pounds per square inch. This happens in a radial aircraft engine at full power, roughly 50 times every second. The spark plug must survive this, hour after hour, without the ceramic insulator cracking from thermal shock, without the electrodes burning away, without the assembly overheating to the point where it glows and ignites the mixture prematurely. And it must do this while staying within a narrow temperature band. If the firing end runs too cold, fuel and lead deposits build up and foul it, shorting out the spark. If it runs too hot, it causes preignition, which can destroy the engine. The spark plug must thread this needle, staying hot enough to burn off deposits but cool enough to avoid preignition inside a combustion chamber that is trying to cook it 50 times a second for hundreds of hours. The narrow temperature band that a spark plug must operate in is called its heat range, and managing the heat range is the central art of spark plug design. The heat range is determined primarily by how quickly the plug can conduct heat away from its firing end and into the cylinder head, where the engine's cooling system can carry it away. A plug that conducts heat away quickly stays cooler and is called a cold plug. A plug that conducts heat away slowly stays hotter and is called a hot plug. By changing the length and shape of the ceramic insulator nose, the designer can lengthen or shorten the heat path and tune the plug to run hotter or cooler. The right heat range for any engine depends on how that engine runs. An engine that runs hot needs a colder plug, one that sheds heat quickly. An engine that runs cool needs a hotter plug, one that retains enough heat to burn off the deposits that would otherwise foul it. The problem with the R-3350 was that it did not run at one consistent temperature. It ran murderously hot on the rear cylinders during takeoff and climb, when the engine was at full power and the cooling air had not yet reached full effectiveness. And it ran cool and rich during the long, high-altitude cruise portions of a mission. The same engine, in the same mission, demanded a cold plug at one moment and a hot plug at another. No single fixed heat range could be perfect for both. The spark plug designers had to find a compromise heat range that would survive the murderous heat of takeoff without pre-igniting and still run hot enough during cruise to resist the lead fouling that the rich mixture produced. Finding that compromise for the specific and brutal conditions of the R-3350 was a major engineering challenge. The lead fouling problem deserves its own explanation because it was the single most common cause of spark plug failure on the R-3350 and on every other high-performance aircraft engine of the war. The aviation gasoline that powered American aircraft was high-octane fuel, and its high-octane rating was achieved partly through the catalytic cracking process and partly through the addition of tetraethyl lead, an anti-knock compound that allowed the fuel to resist detonation at high compression and high boost. Tetraethyl lead was essential to the performance of the engine, but it had a side effect. When the fuel burned, the lead did not simply vanish. It formed lead oxide and lead compounds, and under the right conditions, those lead compounds deposited themselves as a hard crust on the inside of the combustion chamber and, critically, on the firing end of the spark plug. The lead fouling was worst under specific conditions, and those conditions occurred constantly on B-29 missions. The problem arose when the engine ran at low operating temperature with a rich fuel mixture. Under those conditions, the lead did not fully vaporize and pass out through the exhaust. Instead, it condensed and deposited on the relatively cool firing end of the spark plug, building up a hard, electrically conductive crust that eventually bridged the gap between the electrodes, shorting out the spark and stopping the plug from firing. The B-29, with its long cruise segments at high altitude with rich mixtures, and its tendency to run the rear cylinders cool during certain phases of flight, was a lead-fouling machine. The plugs fouled, the engine misfired, the power dropped, and the ground crews had to pull the fouled plugs, clean them or replace them, and start over. The lead fouling was a direct consequence of the high-octane fuel that gave the engine its power. The fuel that made the engine strong also fouled the plugs that the engine needed to run. The spark plug had to be designed to resist this fouling as much as possible, to run hot enough at its firing end to keep the lead vaporized and flowing out the exhaust rather than depositing on the plug. To understand why the spark plugs had such a hard life, you have to understand the engine they lived inside. The Wright R-3350 duplex Cyclone was the most powerful and most ambitious production aircraft engine of the early war years. It was an 18-cylinder, twin-row, supercharged, air-cooled radial, displacing nearly 3,350 cubic inches, which is about 55 liters. Its development began in the mid-1930s, when Wright Aeronautical followed Pratt & Whitney's lead in developing larger engines based on the earlier Cyclone series. The R-3350 emerged as the highest displacement production engine in the world at the time. In its early forms, it produced 2,000 horsepower at a time when half that figure was respectable for a production Rolls-Royce Merlin or Allison 512. The engine's development was troubled and slow. In 1939, for reasons that have puzzled historians ever since, Wright Aeronautical diverted much of its best engineering talent to the development of an enormously complex 42-cylinder liquid-cooled engine called the Tornado, which never entered production. This diversion starved the R-3350 program of the engineering attention it desperately needed before the war. Then, in 1940, when the Army Air Corps issued the requirement for the long-range bomber that would become the B-29, and 3 of the 4 preliminary designs specified the R-3350, the engine suddenly became the single most important aircraft engine program in the country. The engineers were reeled back to the R-3350, but the years of neglect could not be made up overnight. The engine went into the B-29 still immature. By 1943, the B-29 was flying with R-3350 engines, and the engines remained temperamental, with the rear cylinders tending to overheat badly, partly because of inadequate clearance between the cylinder baffles and the cowling. The R-3350's overheating problem was the defining flaw of the early B-29 program, and it was directly connected to the spark plug problem, because heat was the enemy of both the engine and the plugs. The rear row of cylinders, the 9 cylinders at the back of the twin-row engine, received cooling air only after it had already passed over the front row, by which point it was hotter and moving more slowly. The rear cylinders, especially the upper ones, ran dangerously hot. Hot weather and poor runways in the Pacific and in the China-Burma-India theater forced the use of extremely high power settings for takeoff and climb, which generated enormous heat. And the need to close the cowl flaps to reduce drag at high altitude trapped that heat inside the cowling. The combination produced cylinder head temperatures that pushed the engine and the spark plugs inside it past their safe limits. The consequences were severe. The engines tended to swallow valves, the exhaust valves overheating and failing, and being drawn into the cylinder, destroying it. The magnesium crankcase, used to save weight, could catch fire, and a magnesium fire burns at a temperature high enough that water makes it worse rather than better, splitting into hydrogen and oxygen that recombine explosively. B-29s were lost to engine fires that burned through the wing spar before the crew could put them down. The 5 upper cylinders of the rear row needed their spark plugs replaced every 25 hours of engine time on the early engines, and the entire engines were sometimes replaced every 75 hours. The R-3350 was fortunate to survive for an average of 265 hours before being thrown away. The spark plugs lived inside this furnace, on the hottest cylinders, and they had to keep firing through all of it. The heat that swallowed the valves and melted the engines also attacked the spark plugs, and the plugs had to be tough enough to take it. The crisis of the R-3350 engine and all its associated problems, including the spark plug and cooling problems, came to a head in the winter of early 1944. In an episode that became known as the Battle of Kansas, the B-29 was being rushed into service, and the airplanes coming off the production lines were riddled with defects and incomplete modifications. Thousands of engineering changes had been identified that needed to be incorporated into the aircraft before they could be sent into combat. The work had to be done immediately, in the field, in the brutal cold of the Kansas winter, on the windswept ramps of the Boeing plant at Wichita and the surrounding modification centers. Thousands of technicians worked outdoors, in the bitter cold, remanufacturing Superfortresses that had just been built. They tightened baffles, modified cowlings, replaced and adjusted components, and worked through the endless list of changes that the troubled engine and airframe demanded. The R-3350 was forced through an almost unbelievable 48,500 engineering and tooling changes over the course of its early development, and many of those changes were being incorporated in the field during the Battle of Kansas. The deployment schedule held firm despite everything. The first B-29 sends, each with a spare R-3350 slung in its bomb bay, reached China on April 24th of 1944. The airplanes were ready, more or less, but the engines were still temperamental, the cooling was still marginal, and the spark plugs on the rear cylinders were still fouling and failing and demanding constant replacement. The Battle of Kansas got the airplanes into the war. It did not solve the underlying engine and component problems, which would continue to be worked on throughout 1944 and into 1945. One of the cruelest aspects of the early B-29 spark plug problem was purely a matter of access. The early cowlings on the R-3350 installation were designed too tightly, with inadequate airflow, and critically, they lacked proper access doors for spark plug maintenance. On a well-designed engine installation, a ground crewman can reach the spark plugs through hinged access panels in the cowling, pull and replace the plugs, and close the panels, all in a reasonable amount of time. On the early B-29, the cowling design was so tight that reaching the spark plugs on the rear cylinders often required removing the propeller and stripping away major sections of the cowling first. A job that should have taken 20 minutes could consume hours. This access problem multiplied the labor cost of the spark plug fouling problem enormously. It was bad enough that the upper rear plugs needed replacement every 25 hours. It was far worse that each replacement was a major operation. The ground crews, working outdoors on Pacific Islands, perched on oil drums for lack of proper work stands, in the heat and the coral dust, spent an enormous fraction of their time simply getting access to the spark plugs they needed to change. The cowling design, like so many features of the early B-29, was a consequence of the airplane being rushed into service before its problems had been properly solved. Later, cowling designs incorporated proper access doors and improved the airflow, but the early airplanes, the ones that fought through 1944, made their ground crews work for every spark plug change. Earl Dabney on his oil drum was paying the price every day for a cowling that had been designed in too much of a hurry. The company that made the spark plugs that survived inside the R-3350 was the Champion Spark Plug Company, an American firm that had been in the spark plug business since the early days of the automobile and the airplane. Champion had grown into one of the largest spark plug manufacturers in the world, supplying plugs for automobiles, trucks, and aircraft, and it had deep experience with the specialized demands of aviation spark plugs, which were a far more demanding product than automobile plugs. An aircraft engine ran at high power for sustained periods, at high altitude, with the spark plugs operating continuously at conditions that an automobile plug would never see. Aviation spark plugs had to be more rugged, more precisely made, and more carefully tuned in their heat range than any automotive plug. Champion's aviation spark plug business required the company to master several difficult materials technologies. The ceramic insulator, which had to withstand both the thermal shock of the firing cycle and the high voltage of the ignition system, was the most critical. Early aviation spark plugs had used mica as an insulator, built up from many thin layers of the mineral, because mica could withstand high temperatures and high voltage. But mica insulators were fragile and difficult to manufacture to consistent quality. Over the course of the 1930s and into the war years, the industry transitioned to sintered ceramic insulators made from aluminum oxide and related compounds, materials that could be manufactured to precise shapes and that offered better thermal and electrical properties than mica. These advanced ceramic insulators were one of the keys to making a spark plug that could survive the conditions inside a high-performance engine like the R-3350. The ceramic had to conduct heat at exactly the right rate to maintain the proper heat range, withstand the thermal shock of 50 firing cycles per second without cracking, and insulate tens of thousands of volts without flashing over. Getting all of this right, in a piece of ceramic the size of a thumb, was the central achievement of the aviation spark plug industry. The electrodes of the spark plug presented their own metallurgical challenge. The center electrode and the ground electrode were the two pieces of metal between which the spark jumped, and they lived right at the firing end of the plug, exposed to the full heat and chemical assault of the combustion process. The electrodes had to resist erosion, because every spark physically eroded a tiny amount of metal, and over millions of sparks, this would widen the gap until the plug stopped firing. They had to resist corrosion from the combustion byproducts, including the aggressive lead compounds, and they had to resist the heat, maintaining their shape and properties at temperatures that approach the melting point of many common metals. The aviation spark plug industry developed specialized electrode alloys to meet these demands. Nickel-based alloys were the standard, offering a good combination of heat resistance, corrosion resistance, and erosion resistance at an affordable cost. The massive nickel alloy electrode became the workhorse of aviation spark plugs, offering a long service life under most conditions. For the most demanding applications, the industry would later develop fine wire electrodes made from precious metals like platinum and iridium, which resisted erosion far better, though at much higher cost. During the Second World War, the massive nickel alloy electrode was the standard for engines like the R-3350, chosen for its combination of durability and manufacturability at the enormous production volumes the war demanded. The electrode metallurgy, combined with the ceramic insulator technology and the heat range tuning, made up the package of technologies that allowed a champion aviation spark plug to survive inside the cylinders of the R-3350. The phrase "surviving 2,000 degrees" is not an exaggeration. The flame temperature inside the combustion chamber of a high-performance gasoline engine at the moment of ignition reaches well over 3,000 degrees Fahrenheit, and the sustained temperature that the firing end of the spark plug experiences, averaged over the combustion cycle, can approach or exceed 2,000 degrees Fahrenheit on the hottest cylinders under the hardest operating conditions. This is hotter than the temperature at which steel begins to glow red and lose its strength. It is approaching the temperature at which many metals melt, and the firing end of the spark plug, the ceramic insulator nose, and the electrodes had to sit in this environment continuously and keep functioning. The way the spark plug survived was through careful management of the heat path. The heat that flowed into the firing end had to flow back out, conducted through the ceramic insulator and the steel shell into the cylinder head, where the engine's cooling air carried it away. If the heat flowed out at the right rate, the firing end stabilized at a temperature that was hot enough to burn off deposits, but cool enough to avoid melting or preignition. The entire design of the plug, the length and shape of the insulator nose, the mass and material of the electrodes, the thread and seat that connected the plug to the cylinder head, was tuned to manage this heat flow. The champion engineers had to design a plug whose heat path would keep the firing end in the survivable band, even on the murderously hot upper rear cylinders of the R-3350, even during the high-power takeoff and climb, when the engine generated the most heat and the cooling was least effective. This was the engineering achievement at the heart of the story. Not the invention of the spark plug, which was old technology, but the precise tuning of an existing technology to survive a new and brutal extreme. The plug that could survive 2,000 degrees inside an R-3350 cylinder was the product of decades of accumulated aviation spark plug engineering, pushed to its limit by the demands of the most powerful engine in the world. The men who actually dealt with the spark plugs, day in and day out, were the ground crews, and their work was among the hardest and least recognized of the entire air war. The B-29 ground crews in the Pacific worked outdoors, in tropical heat and humidity, on coral hardstands, often without proper equipment. They perched on oil drums because there were not enough work stands. They pulled cowlings and propellers to reach the spark plugs. They pulled the fouled plugs, inspected them, cleaned the ones that could be cleaned, and replaced the ones that could not, and reinstalled them, torquing each one to the correct specification, gapping each one correctly, indexing them so that they were not reinstalled in the same position they had come from. A single engine had 36 plugs. A single B-29 had 4 engines, 144 plugs. A bombardment group had dozens of B-29s. The number of spark plugs that had to be maintained, cleaned, and replaced across a B-29 operation was staggering, and every one of them was handled by a ground crewman working in difficult conditions. The ground crews developed an intimate, practical knowledge of the spark plugs and their failure modes. They learned to read the plugs, to recognize lead fouling by its hard gray-white crust, oil fouling by its wet black deposit, and overheating by the clean white or reddish appearance of a plug that had run too hot. They learned which cylinders fouled fastest and watched them most closely. They learned the tricks of the trade, the anti-seize compounds, the cleaning techniques, the inspection methods. They were, in their way, the final and most important link in the chain that kept the spark plugs working and the engines running. The champion engineers designed the plugs, the factories built them, and the ground crews installed and maintained them. And only when all three did their jobs correctly did the engine fire reliably and the bomber fly its mission. The ground crews are even less remembered than the engineers, but the engines ran on their labor as much as on the spark plugs themselves. Over the course of 1944 and into 1945, the various problems of the R-3350, including the spark plug fouling problem, were gradually attacked through a combination of engineering changes. One of the most important was the transition from carburation to fuel injection. The early R-3350 used a downdraft carburetor which mixed fuel and air before distributing the mixture to the cylinders. The carburetor did not distribute the fuel evenly, so some cylinders ran richer than others, creating hot spots and contributing to both the overheating and the fouling problems. Some cylinders got too much fuel, ran rich, and fouled their plugs, while others got too little. The solution was direct fuel injection, which delivered a precisely metered amount of fuel to each cylinder individually, ensuring an even distribution. Fuel injection improved the cooling by evening out the combustion, and it reduced the spark plug fouling by ensuring that no cylinder ran excessively rich. The change to fuel injection was one of the most significant improvements made to the R-3350 during the war, and it addressed both the overheating and the fouling problems at their common root. The uneven fuel distribution, combined with the other improvements, the revised cowlings with better airflow and access, the tighter baffles, the better exhaust collectors, the improved cylinder head temperature monitoring, and the shift to lower altitude bombing tactics that reduced the engine stress. The fuel injection helped to gradually tame the R-3350. The time between overhauls rose from 100 hours early in the program to 400 hours by the end of the war. The engine that had been a temperamental killer in 1943 and 1944 became, by 1945, and especially after the war, a reliable and even excellent engine, used in airliners and military aircraft for years afterward. As the engine improved, the spark plug situation improved with it. The fuel injection reduced the fouling by evening out the mixture. The improved cowlings made the plugs easier to reach. The better cooling reduced the thermal stress on the plugs. And the spark plugs themselves continued to be refined, with improved insulator materials, better electrode alloys, and heat ranges more precisely tuned to the specific conditions of the engine. The transition from mica to sintered ceramic insulators, which was largely completed during this period, gave the plugs better thermal performance and more consistent manufacturing quality. The plugs became more durable, more resistant to fouling, and longer lived. The combination of a better engine and better plugs meant that, by the later stages of the war, the spark plug maintenance burden on the ground crews, while still substantial, was no longer the desperate, every 25 hours crisis it had been on the earliest engines. The plugs lasted longer between replacements. They fouled less often. They were easier to reach when they did need attention. The R-3350, which had started its operational life as an engine that ate spark plugs and swallowed valves and caught fire, became a manageable and then a reliable engine, and the spark plugs that lived inside it became a manageable and then a routine part of its maintenance. The crisis of the early B-29 spark plug was solved not by a single dramatic breakthrough, but by the steady accumulation of improvements in the engine, in the cowling, in the fuel system, and in the plugs themselves, each one chipping away at the problem until it was no longer a crisis. This is how most real engineering problems are solved, not by a single stroke of genius, but by the patient accumulation of many small improvements, each one making the next one possible. The Champion Spark Plug Company emerged from the Second World War as one of the major suppliers of aviation spark plugs in the world, a position it would hold for decades afterward. The aviation spark plug business that Champion had built, refined under the brutal demands of wartime engines like the R-3350, continued into the post-war era and into the present day. The company's aviation division, eventually known as Champion Aerospace, remained a leading manufacturer of aviation spark plugs, magnetos, and ignition systems. Today, Champion Aerospace, based in Liberty, South Carolina, continues to manufacture aviation spark plugs using technologies that descend directly from the wartime work: the sintered ceramic insulators, the nickel alloy massive electrodes, and the precise heat range tuning that had been refined under the pressure of war. The basic technology of the aviation spark plug, established and refined during the war years, has remained remarkably stable. Modern aviation spark plugs still use the same fundamental architecture: a center electrode in a ceramic insulator in a steel shell with a ground electrode. They still come in massive nickel alloy versions and fine wire precious metal versions. They still have to manage their heat range, resist lead fouling, and survive the brutal conditions inside a combustion chamber. The lead fouling problem, in particular, remains a live issue in aviation today, because aviation gasoline still contains tetraethyl lead, and pilots and mechanics still deal with lead-fouled plugs using techniques that would be recognizable to Earl Dabney on his oil drum on Saipan in 1944. The wartime aviation spark plug technology was so fundamentally sound that it has carried forward, with refinements, for 80 years. The lesson of the B-29 spark plug is a lesson about the importance of the small components, the parts that nobody thinks about in determining whether the big systems work. The B-29 was a magnificent airplane, the most advanced bomber of its era, and the R-3350 was the most powerful production engine in the world. But the airplane could not fly, and the engine could not run without spark plugs that worked, and the spark plugs turned out to be one of the hardest parts of the whole system to get right. The most powerful engine in the world was limited, in part, by the difficulty of making a piece of ceramic and metal the size of a thumb survive inside its own cylinders. The grand achievement of the B-29 rested on the humble achievement of the spark plug. This is a pattern that runs through all of complex engineering. The performance of a system is limited by its weakest or most stressed component, and that component is often something small and unglamorous. The aircraft engine is limited by its bearings, its valves, its seals, its spark plugs. The grand vision of the designers depends on the humble competence of the component engineers, the metallurgists, and the ceramic specialists who make the small parts that the big systems depend on. The B-29 program understood this, eventually, and devoted enormous resources to getting the small components right. The lesson is that there are no small parts in a complex machine. Every part is essential, and the failure of the smallest part can ground the largest airplane. The spark plug that Earl Dabney held in his hand on Saipan was as essential to the mission as the bombs in the bomb bay, and the engineers who made it survive 2,000 degrees were as essential to the war as the men who flew the airplane. In a war decided by what worked was the spark plug that survived 2,000 degrees. It was the size of a thumb. It cost a few dollars. It was treated as a consumable, thrown away by the thousands, logged in and out by ground crewmen perched on oil drums on coral islands in the heat and the dust. But it sat inside the combustion chamber of the most powerful and most overheated engine in the world, and it fired 50 times every second, while the metal around it glowed, and the lead fouled it, and the cylinder tried to cook it to death, and most of the time it kept firing. That was the whole achievement. A piece of ceramic and metal that could survive the inside of a Wright R-3350 cylinder and keep making the spark that the engine needed to run. The engine was famous for its troubles, for the overheating and the swallowed valves and the magnesium fires. The airplane was famous for its missions, for the firebombing of Japan and the atomic bombs. The spark plug was famous for nothing. It did its work in the dark, inside the sealed cylinder where no eye could watch it, and when it worked, nobody thought about it, and when it failed, a ground crewman pulled it and threw it away and put in another one. The champion company that made it is remembered today, if at all, as a maker of automobile spark plugs. The engineers who tuned its heat range and refined its ceramic insulator and chose its electrode alloy are anonymous. But the plug they made was one of the limiting components of the entire B-29 program, and getting it right was one of the quiet achievements that made the airplane possible. In a war fought between industries, the side that could make a spark plug survive 2,000 degrees inside the hottest engine in the world was the side that could fly the most advanced bomber in the world. The Germans and the Japanese had spark plugs too, and their engines ran. But the American aviation spark plug industry, with its decades of accumulated expertise in ceramics and electrode metallurgy and heat range tuning, was second to none. And it produced the plugs that kept the R-3350 firing through the conditions that should have killed it. The plug was small. The achievement was not. In a war decided by what kept running, what kept the R-3350 running, spark by spark, 50 times a second, 265 hours at a time, was the small ceramic and metal object, stamped with the word champion, surviving 2,000 degrees inside a cylinder that was trying to destroy it, and firing anyway. That was enough. It was, in the end, one of the 10,000 small things that won the war.